Um, okay, so it's a great pleasure of mine to introduce Katie Cooper from Washington State University. Before I formalize the introduction, let me first acknowledge the traditional owners of the lands on which all of us meet, and convey our thanks and respect for, in our case, many millennia of custodianship and stewardship of the land, and pay our respects to their elders. And Katie is coming to us from Washington State, which is in the homelands of the Palouse people and the, how do I pronounce that, Katie? Nimipu people and the Nez So we acknowledge the First Nations people from where Katie is speaking from. Okay, so let me tell you a little bit about Katie. She did her undergraduate program in geophysics in Texas, at Texas A&M. She then moved to Rice University, also in Texas, and worked with Adrian Enarek. She completed her PhD in 2005 and then went on to the Carnegie Institute of Washington at the Department of Terrestrial Magnetism there as a postdoc for 2 to 3 years, is that right? Something like that. And then she went to work at the NSF, and the NSF is a little bit different from the ARC, that they actually have positions there which are for, which can only really be filled by academics. And she was the program officer, for the EarthScope program in the year 2007, 2008. And then went on to Washington State University in 2008. She became an associate professor there in 2014, and she's joining us from there today, or this evening for you. So Katie, over to you. Craton stability, tell us all about it, please.
Thank you, and thank you all for inviting me. I'm absolutely thrilled to do this. I was in a meeting earlier today with a bunch of deans. They're trying to get a feed on how people were doing, and they asked what are some of the positive things that have come out of the situation that we're in right now. And I said that the connections to international communities through seminars has really been a huge plus for me. And so it's an example as well of getting to engage with a larger group that I wouldn't necessarily get to on this level. So thank you for this, I really appreciate it. So what I'm going to talk about today is Craton stability, and really the role of thickness within Craton stability. And slight pun in here, with my apologies to Tina Turner, and play on What's Love Got to Do with It. So if you don't know that song, check it out, it's great. All right, so I also want to start off with the recognition of my colleagues. Some of those who are your colleagues as well too, Megan Miller, Rebecca Farrington, and Louie Marazi as well too. For those of you who are early career, I highly recommend finding colleagues who intellectually stimulate you, but also are true friends as well too. And so I wanted to start off with that recognition, because it's an absolute blast to work with these people. So if you remember nothing else from my talk, I really would like you to take away with this kind of pithy statement that lithospheric thickness shapes cratons literally, but it's also shaping their trajectory and is connecting to some of the pivotal moments in Earth's history, and what I'm finding to be really interesting and surprising ways. So start off with what is a craton, and I thought about being really clever and setting up a Zoom poll in advance to get votes on what people think is a craton, because the more I speak to people with different backgrounds about what a craton is, I find that we often have very different ideas. But I came to my senses and realized that I can't really get Zoom polls to work in my class, so perhaps I shouldn't try it within a presentation. So instead, I'm going to provide you the definitions of a craton. So the classic definition are that Cratons are regions of the Earth's crust that have not undergone deformation in long periods of geologic time. And I'd like to think as there's a more modern definition of the regions of the crust and the lithosphere that has not undergone deformation in long periods of geologic time. And I find this delineation and kind of this progression of this meeting really telling. And it's really telling with how we're then rethinking about what's then forming Craton stability. And this gets back to some of the big first order observations of Cratons and about them. So these connections between the surface and the lithosphere come up. And so these are two different global maps showing observational clusters. And the one at the top is being driven from surface observations down into the crust that way, where then these authors have then grouped together regions that are similar with these varying different names that they prescribe to them. The one down below is taking more of a bottom-up look into the continents, looking from about 350 kilometers up to say, what are similarities that we see within seismic observations? And what I think is interesting, and we did intentionally color these way, is to look at the similarities between the groupings that are happening from surface observations coming down and from those coming up, is that they do seem to overlap in regions, in particular these regions of the Craton. So hinting at, again, that there seems to be a connection in between the surface expression as to what we're seeing, and we've recognized as these are the regions of long-term stability, as well as then happening down at depth. And another way to look at this as well is if you plot up and compare the thickness of the crust as well as the thickness of the lithosphere, you can see also similar groupings coming out where you then see these regions of similarity where then you have Cratons. So again, hinting at that the lithosphere is really playing a big role within the Craton, the nature of the Craton itself. And it's this thickness of the Craton that I'm going to argue to you is playing probably one of the first order controls on Craton stability and other things too. So this is then a map of the depth to the LAB boundary, lithosphere cenosphere boundary. And you can see in these regions that we're popping out in those clustering methods, as well as then the ratio between the crustal and lithospheric thickness are happening in these regions of really thick lithosphere that are laying underneath the Cratons. Now, lest you think I only talk to seismologists, we're also seeing, again, evidence coming from geochemistry and from xenoliths indicating this thick lithosphere is really one of the first order observations of Cratons themselves. Another thing that I think that's important to point out is that long periods without deformation, what we're talking about is that if you're looking at then the ages, and this is a plot showing various different events within the Earth, but here are ages that span then for keels, and you'll see that these ages are quite old. So what I think is interesting is that though it seems to be that these thicknesses are really playing an important role in making a Craton a Craton, we almost argue that Cratons are stable despite their roots. But really, it's their roots that are doing the work. And the reason why we argue that they're stable despite their roots is, as I showed before, is those roots seem to be pretty old. Now, in addition, they're also cold, and when you know they're cold, looking at surface heat flux values, as well as, again, we're picking them up within seismic tomography, indicating that not only are they compositionally different, they're also cold as well too. And then looking at those xenoliths, they're also telling us that, again, there's cold temperatures extending into the root. So if they're old and cold, we would expect there to be sufficient thermal contraction that these would be dense and then want to return back into the mantle. So then not necessarily being stable. But again, it is the roots that are then supplying that stability to overcome that tendency of something being cold and contracting and becoming more dense. And this idea of how do we compensate for the old and cold, some of these early ideas were coming from early work by Thomas Jordan, summarized within what's known as isopycnicity. And this is a hypothesis that there is a positive chemical buoyancy to the material that makes up lithospheric roots that is exactly offsetting the negative thermal buoyancy. And so this is a plot here of conceptually what it means to be isopycnic, that this thermal difference that you would expect since it's colder than the surrounding material would be exactly offset by a compositional difference that's then driving buoyancy. So this would then leave it net neutrally buoyant. However, it's interesting is that cratons aren't exactly quite isopycnic. So these are plots of magnesium numbers against depth or pressure, if you prefer to look at this way, for different zeniths from different cratons around here. And what's plotted out here is how you would expect the magnesium number to change with depth if indeed they were isopycnic. And you'll notice that really only one area or one craton seems to follow that trend with it too. And that really the scatter here is not actually representative of that line. So I tried to find a summarizing table or figure that described all of the different ways that we give to craton stability. I couldn't find it, so then I made my own cartoon. But really, there are a lot of different ideas that go into what's making a craton stable. It's connected to the composition, like we talked about before, of, okay, we know these would be thermally unbuoyant. I don't know. They would want to go down, so then if you have a composition to offset it, that would then provide you stability. We then can also say, well, they're rheologically strong in that they have very high viscosities relative to the surrounding material, because perhaps they were formed under conditions which would lead to dehydration, which would enhance the viscosity. Or another rheological strength is that they could have high yield strength. Or you could then say, well, you know what, maybe they're only marginally stable, and it's just that they're next to weaker regions, and those weaker regions are then taking up most of the deformation. But really, what all of these have in common is that they're all connected to the thickness of that root as well. And so when we start expanding on our ideas about what's craton stability, often we turn to stability regime diagrams to explain it. So before I start showing you the ones that demonstrate craton stability as driven by buoyancy and yield strength, I wanted to just take a step back real briefly and talk about how to read a stability regime diagram. So what we do is we build out a parameter space. And so in this case, we plotted down here property A, which has values that range from 10 to the 5th to 10 to the 10th. And against then a property B here, which has values that range from 0 to 250. Then we've plotted up a hypothetical curve here. That's then based on some sort of theory that then tells you that for the conditions that are within this range, we would expect one behavior. Or for the conditions within this range, we would expect another behavior. So this line demarcates of when we expect behavior 1 to happen or behavior 2 to happen. So if we're then doing this for what would then promote stability for cratons, and we start thinking, okay, well, we can do this for buoyancy because we can set up a very simple force balance that in order for you to resist being entrained in a downwelling and becoming unstable, then we can then say the buoyancy of that material must exceed the thermal boundary, the strength of the thermal boundary. And so then if we come up with this theoretical relationship here, which then states the buoyancy ratio, which I've given in this equation here, which is looking at the differences between the compositional buoyancy on the top and then the thermally driven contraction on the bottom here too. We can say that this times the thickness, which would give you the integrated buoyancy of the entire root, in order for it to be stable, it has to be greater than the Rayleigh number to the -3rd value. Now the Rayleigh number is a non-dimensional number that is representative of convective vigor. So the higher the Rayleigh number, the more vigorous of the convection. The lower the Rayleigh number, the more sluggish the convection with it too. So that line, or this condition, is then plotted along here. Everything within this parameter space would then be stable. Everything below this line in this parameter space would experience deformation of some sort. All right, so then this allows us to explore this idea of what does it mean to have a buoyancy-driven stability for a craton. And it goes back to, or helps me like connect back into stability for all of those ways that I pointed out are connected to the craton thickness itself. So I've plotted up that same line that I showed before. Again, remember, when you're to the right or above this line, we're in stable regimes. When you're below this line or to the left of it, you're in deforming spaces. That's the behavior you would expect. So I've done this for different compositions with on here too. But you'll notice that for a single Rayleigh number, and I should point out, you can use the Rayleigh number for a proxy for mantle dynamics or also then time. If you make the assumption that the Earth was hotter in the past, you would expect to have higher Rayleigh numbers. So this is also a proxy for geologic time, if you want to think about it that way. Or it can also be a proxy for mantle dynamics regionally. All right, so if you say you're at 1 Rayleigh number and you have a craton, and if you say then it creates, or a craton that's, let's say you have 3 different cratons, why not? All right, so you have a craton that's of this composition, a craton that's of this composition, and a craton of this composition. So you could have a craton of this composition and it would be 50 kilometers or above 50 kilometers and it would be stable. But however, if you have then a craton of this composition, there's no way it would be stable at 50 kilometers. This stability wouldn't be achieved until you're above 150. So the stability is achieved at different thicknesses for different compositions. So yes, it's important to be buoyant, but also you need to be thick on top of it. Which brings me to another point that I want to make using these stability regime diagrams, is we can talk about stability, but we should also be talking about longevity. And one of those things that I pointed out where I showed you the ages of the roots as a first order observation of cratons shows that many of them have been around for billions of years. So that's actually longevity. Stability is really then telling you, are you resisting deformation in the current dynamic setting? But longevity will tell you that you're resisting deformation over a range of dynamic settings. So stability, resist deformation for 1 Rayleigh number. Longevity, resist deformation for a range of Rayleigh numbers. So we can look at these stability regimes thinking about, well, what's going to promote longevity? So now, instead of thinking, we'll look at these different compositions, which become stable at which thickness, let's then think about, what if we had thick lithosphere? And so we had around 200 kilometers. I then can, if I know the composition of it, can say that you can have a stability regime, like for the same composition, that if it's thicker, you're going to be stable for a larger range of Rayleigh numbers than if it's thinner in this case. And this holds true for all the compositions, although that changes between what's stable and what's not does depend on the composition as well. But the overall, the thicker that you are, the longer or the larger range of dynamic settings over which you can be stable. So you have longer, have more longevity in that case. Now let's think about another way that we know that we can provide craton stability. And this is through having stronger yield strength. So again, we can apply another balance, in this case a stress balance, and say, in order to resist deformation, the craton's yield strength can't be exceeded by convective stresses. Convective stresses scale with the Rayleigh number, and the lower the Rayleigh number, the more or the higher convective stresses that you have. because the entire convection scheme is more sluggish, which then is harder to move, which then builds up more stress. So this case, what this line is representing is the point at which the friction coefficient of the value times the thickness of the lithosphere, so the yield strength of the material. In order for stability, that has to be higher than the Rayleigh number to the -3rd value. So within this parameter space, we expect stability for the craton. Within this parameter space, we expect deformation of the craton. And just like before, when we cross over into that stability regime, depends on material properties of the craton itself. And then also then, but the thickness then tells you how long you can be stable for. And so for thicker lithosphere, for the same friction coefficient values, you have much larger ranges over Rayleigh numbers or mantle dynamics over which you're stable. So again, thicker lithosphere is promoting longevity. So then I start wondering, so if we plot up a conceptual diagram here, if we have time increasing in the Earth, then that means that the craton thickness, if they really are long, like they are experiencing longevity, we're then keeping mostly near constant lithosphere with time. And there can be some really interesting consequences of this. So one of the consequences of this is then start thinking about supercontinent cycling. So this is a interesting diagram. So let's take a moment to reorient or to orient ourselves looking at this. And down here in this insert, you'll see that the continents are in a bit of a different configuration in the present day. And this is the configuration of Pangaea. So what the authors did here is they took modern day images of seismic tomography and then rotated them back into the position of Pangaea. What they then noticed is these regions that are thick here, it's been contoured down here. So the darker the blue, the thicker the lithosphere, that they line up in this like this little arcuate shape with it too. And so what they proposed is that then cratons are really then determining what happens during supercontinent cycling. And they're likely controlling the deformation that's happening between the regions, as well as then how it's then splitting back up with it too. And so then they're acting as bumper cars during supercontinent cycling, which then smashes material in between it, or then it comes splits apart. Now, another interesting implication of having long-lived thick lithosphere is that this then also controls when continents emerge to become subaerial rather than submarine during early Earth. And this is a really interesting idea that kind of blew my mind a couple of weeks ago when Sinti gave a talk during our seminar series. And he made the argument that based on the crustal thickness of cratons, their elevation is too low. And so then he and his co-authors went through a really interesting scaling exercise where they then determined when continents would then move above sea level and become exposed based on this during time. So each one of these contours here represents a different crustal thickness. This dashed line here is then where sea level, so your elevation is 0. Put that in here too. So you'll notice back in time, the continents were below sea level. And if it wasn't until they started cooling, and if you want to use the 35 kilometers, which is around the age, that they then started to pop up out of the seas and be exposed. Now, the reason why this happens is because we then have these thick continental or thick cratonic roots. And it has to do with then what thermally happens when you have a big, thick, chemically distinct root. And really what we need to think about when we're conceptualizing cratons is that we have a chemical boundary layer, so something that has a distinct chemical signature to it that's embedded within a thermal boundary layer, which then the thermal boundary layer is then being controlled by the cooling of this region. And between the two, you have what's known or termed as a convective sublayer, which this region in here is cooler than the mantle that's surrounding it, but likely of the same composition within it too. And these two are connected, and the thicker the chemical boundary layer, that chemical thickness or that root that you have, the more it takes up the thermal boundary layer. And so what's plotted up here, again, is chemical boundary layer on the x-axis, and this is then plotted up against the ratio of thermal to chemical lithosphere. So the ratio of those two thicknesses. So as again, you increase the root thickness, you're then decreasing this ratio until it starts approaching 1, where then the chemical boundary layer is really then swamping up and taking up the thermal boundary layer. What this means is then, if this is something that is old and long-lived, is then we've now made the thermal boundary layer being that thick, old, and long-lived as well. Which, if you remind yourself back to what I said before, if cratons are old and cold, they should have a down pole with them. And indeed, they are having a down pole with them that keeps them pulling down like you would pull down an anchor until the mantle cools enough to where then the balance between the thermal buoyancy and the chemical buoyancy is such that they can then rise back out of the sea and then become exposed. Now with this, let me take a water before I get into the really cool stuff. With this, that would be a somewhat catastrophic climatically transition. This would also have a lot of implications for the style of continental weathering as well too. And what they then further argued is that this probably also connected back into setting the stage for the Cambrian explosion. Now, I don't know if you caught the reference on that last slide, but that was my very first paper. And the fact that my very first paper had implications for the appearance of trilobites, I think that's how you know that you've made it. So I feel like I've finally made it now. But that's a really fascinating result. So it's a first order characteristic, craton thickness. It's the primary control on stability as well as longevity. And it also then impacts the trajectory of what's happening to continents from that point on. It's connecting back to supercontinent cycling. It's connecting back to when they appear out of the oceans, which then that sets the stage for weathering, and maybe even setting the perfect conditions so that you can have trilobite friends. We'll see. So if this is like a first order kind of control, this leads me kind of to my next part of the talk, is then to start pondering, well, why do we draw this shape for cratons when we're drawing it? If it really is that they're just these fixed regions, why are we giving this trapezoidal shape to it, with it? And this is even more kind of interesting, is then the more that we have been looking at cratons and we've increased our seismic observations, we're seeing that there's a lot of different shapes of cratons. And they can have shapes that are a bit more gradual, so that kind of interesting trapezoid look over here from Morocco area, or they can be very dramatic change into the thick lithosphere that you can see within Western Canada here, where you're going from not really much of a lithosphere to then a very thick, abrupt lithosphere. So you have then something that looks very steep and vertical almost. They can also have stepped increases as you moved into the Craton. So as I'm sure you are all very familiar with, the surface wave tomography of Eastern Australia is then showing this nice stepped increase too. You can also see a stepped increase in northern South America. As we're moving into the shield, we see then thicker lithosphere. And what's interesting about this is you'll notice that the stepped increase is right next to a subduction zone in this area. And this is interesting, and we'll come back to this in a second. We also know from geodynamic models that the shape of cratons or those margins can evolve, and they can either be preserved or modified depending on the rheology of the cratonic lithosphere. So these are models from Curie and Van Wyck, where they embedded a craton here with a vertical margin. And you'll notice that this vertical margin can persist for 100 million years if it's rheologically strong enough. If not, and on the left, this is for weaker rheology, you'll see that then that shape is evolving into something that looks a lot more gradual, like we typically show, but then eventually the entire thing pancakes out and you lose a considerable amount of thickness in this case, or that. So if we know that they can be preserved and we know that they can be modified depending on the rheology as well as the dynamic settings, then it starts making us really wonder even bigger questions of what is happening when we do see these interesting shapes. Are these shapes helping to control deformation? Are they potentially driving mantle flow against them? And can that feed into their own potential demise? Because remember, as I pointed out, thickness is one of those first order controls and stability. So then if you're saying modifications to the thickness, can that then feed in to Craton instability? So to test this idea, we wanted to return back into that interesting tectonic setting that I hinted at before, where we have this stepped increase in cratonic thickness for Northern South America here. And we've butted up against the subduction zone as well. Or over in the Western Africa, we see a more gradual increase in thickness. And it also is butted up next to an arc. And what's plotted on both of these are splitting patterns, which are then indicating that there does seem to be mantle flow that's being directed right along these. Now this makes sense if you're right next to a subducting slab. So we know that subducting slabs are driving large mantle flow. And so is that large mantle flow being directed up against the craton margin because of these shapes? And if so, is that then feeding into the stability of these cratons themselves? So since this is a testable idea, this means I'm going to test it with some models. So this is the geometry of the setup that we came up with. So where we're putting a craton, this is looking bird's eye view down into the setup that we used. So we have a model craton in gray here. We've abutted it next to a slab that's experiencing rollback. And then the rest of the material is average mantle or average oceanic lithosphere. And we wanted to test out, well, within the setting, what if we tried different shapes to see, again, are some shapes channelizing more? Are they channelizing less? So this is now looking at a side view. You can see the slab here, the thick interior of the craton here. I've sketched out the one for the tiered shape as well, but I've also outlined the other shapes that we explored. So we explored that gradually sloping increase in thickness, so something that looks more like a trapezoid. We call this margin the diagonal shaped margin. And then we also considered those dramatic increases in thickness as outlined in here. And we've said, okay, well, what if we have dramatic straight vertical, and that's what you call the margin that's further away from the slab, allowing there to be a channel in between the slab and the craton? Or what if we then put the straight vertical shape right up against the slab as well too, to see what is the control of the channelization or the size of the channel on it too. So we have this one here that we call straight proximal because it's right next to the slab. This one is straight distal because it's further away from the slab. Diagonal, and then tiered shape as well. So we ran a series of instantaneous flow models using Underworld 2 at high resolution. We used a temperature field to initialize the models, and we used half-space cooling models for prescribed craton thickness, oceanic plate age, and subducted plate age. We then used free-sit boundary conditions on all of the walls, and then employed a temperature and strain rate dependent dislocation and diffusion creep rheology with it too. All right, so to really understand what was happening within the flow fields, we looked at a set first of the Craton only flow fields. And we did this for all of the different Craton shapes. So what we're looking at here is, and we're looking at the Craton here, so a bit of a side view. You notice the Craton is outlined in gray. There's also some red regions there. Those are dissipation contours. All right, so what's plotted up here, these small things, those are actually the velocity vectors. And you can see that they are scaled up by 10 times, because if we didn't do that, you would be like, I'm sorry, Katie, I don't see anything on this slide. That's because they're incredibly small. So the flow field that's associated with Cratons is just small scale convection along the Craton edges, so very small scale. You can also, we decided to look from the devil's eye view, so straight up, looking underneath the Craton margin to then really get a good view of what's happening along the margin itself. And again, from this view, you can see there's these small amounts of flow that's happening right along those edges, but again, they're incredibly small. Now compare this to the slab only flow field. These are not scaled up, they're considerably larger. This is then the slab only model, and we see this large toroidal motion that's being driven by the slab rolling back. And we can see this again from below. If you're having a hard time orienting yourself with this devil's eye view, imagine you're standing down here and looking up. So now looking at the combined flow fields, where we then have both the Craton and the slab together. And we can see, indeed, it does seem to be that toroidal flow that's being driven by the subducting slab is being channelized right along the Craton margin. Looking at this from below, you can see it being moved right along that margin. All of that small scale convection has been swept up into the larger mantle flow. And then looking at all of the different shapes, so we have the diagonal shaped here, straight proximal here, so that's where the slab and the Craton are right next to each other. There is still a bit of a channel there, it's really small, but there's a channel within the third dimension. And then we have straight distal, where then the Craton straight edge is further away from the slab. And you can see in all of these, you have channelization that's happening within the margin in between the Craton and the slab. But the level and the amount of channelization depends on then the shape of the margin, which makes sense because that is then controlling the cross-sectional area of the margin, so how much material you can move through there. And so that really does make sense when you look at the straight proximal, where that channel is very small, and again, you don't see as much flow happening in there. So cool. One idea is correct. Indeed, the Craton margin itself can then help drive flow right along its path. But what does this say then for the stability of it? For this, we then wanted to look at a different observation rather than just the flow fields. So in this case, we wanted to then look at the strain rate to give us a proxy for potential for deformation. So we then sampled the strain rate using a sampling transect. So now we're looking south into the model. So you can see the outline of the slab here. Then you can see the outline of the tiered Craton margin as well. This blue line, imagine it's coming in and out of your screen. And that is then sampling the strain rate at every location from in front of the slab here, in through the channel, and then all the way into the Craton interior itself. And this is what comes when you take the sampling profiles. So real quickly, before we look at this down below here, let's orient ourselves using this guide up above. And so what we've sketched up here, these are different depths. This is to help give you a sense of where you are along that sampling transect. So this gray line here is the sampling transect itself. And then what we've outlined in these different colors are the cross-sectional geometries of the different Craton margins that we explored. So in red here is the tiered, oh, in red here, sorry. In the red here is the straight distal margin. In the green, we have straight proximal. And then in the orange, we have diagonal. And then the blue, we have tiered shape. So then looking at this, we can then say that the sampling transect will enter the craton at different positions based on the geometry of the shape of the margin. So the sampling transect enters the straight proximal craton at this point Y here, which corresponds to going down here around 2,000 kilometers. But for then the straight distal, it enters the craton at X. And it also enters the diagonal at that point as well too. For the tiered, you'll notice that the transect runs right along the base of this tier and then enters the craton at this point down here. All right, so now we're oriented ourselves. Now let's look at what we plotted at below here. So these are all of these strain rate profiles for the different models. The ones that are in dashed, those are Craton only models. This dashed line here, that's in black, that's then for the slab only model, which then gives you a sense of what are then the strain rates that are associated with that large toroidal mantle flow. The ones that are in solid, these are all the simulations that have the Craton and slab together within the model. So we can then see when we're comparing then the Craton only versus ones with Craton and slab, there is a big jump within the background strain rate that's occurring within these simulations. This makes sense because again, before we only had really small flow fields. All right, so what's interesting though to me is that we see this overall increase in strain rate, but as you start approaching the Craton and moving towards those channels, you see a sharp increase in the strain rate. Now, depending on the Craton shape, that strain rate will decrease either dramatically or gradually. It decreases dramatically for the straight vertical margins. As soon as you enter into the Craton, this increase in strain rate has been dampened out, regardless of whether or not you have a channel. Now compare this to those that have progressively thickening, so that diagonal shape or that tiered shape. And you'll notice that that increase in strain rates extend into the Craton interior itself. And again, this holds for the diagonal as well as then for the tiered shape as well too. So if those increased strain rates are extending into the Craton itself, that means that there's an increased likelihood for deformation of that Craton. So this is already telling us that it seems that Craton stability is also connected to shape, which makes sense because shape is then controlled by the Craton thickness or vice versa. But some shapes are much more stable than others. Now, what's also interesting about this is then if we're extending higher strain rates into these regions that are progressively thickening, would they start deforming and move into a runaway process until they move to something and change into something that's more stable or a vertical shape? So then have we set these up to progressively evolve into something that's more of a straight vertical shape? And so to get back to these images that kind of motivated it all, we notice by looking at the splitting patterns, it's like, okay, yeah, not only are we seeing that there is channelized flow happening in these regions, we're also seeing a pattern of going from those increased strain rates associated with this flow to that they're diminishing, but they're not diminishing suddenly. You are seeing them still extend within to the Craton itself. So then we're wondering, are these anisotropy patterns potentially reflecting that there's inward progression of deformation happening within the Craton? And so I want to give you these big picture conclusions. I hope I convinced you that Craton stability and longevity are linked to Craton thickness. The shape, which you can just think of shape as variations in thickness, is also contributing to craton stability, with some shapes that are promoting stability over others. The dependence on shape could cause cratons to potentially progressively erode in a runaway process until a more stable shape has been achieved. But I think it's important that we don't just conclude with conclusions, that we think about what else can we think about with this. So these are things that I'm still curious about. And I think for a larger, for longer talks, this is really what I would like to end with, is then start thinking about, and what I'm thinking about next is, what are the consequences of having long-lived thermal boundary layers that are thick? How is that changing the thermal evolution of the planet? We're kind of short-circuiting some scaling relationships of how we expect convective systems to evolve by having this. And is this helping keep continents around on the Earth? Because this also then feeds back into erosion rates as well too. Or is this even then limiting further continental growth? I don't know. Other questions that I'm still pondering about around shapes is that, what timescales do craton margins evolve or remain stable? And of course, this is an interplay between both the rheology and the shape itself. And then what would be the consequences of that progressive erosion? How could we capture this within the rock record with itself? So I'm just gonna finally conclude that same pithy statement that I opened with, is that lithospheric thickness is shaping cratons both literally, but it's also then figuratively shaping their trajectory, and it's really connecting to some of the real key pivotal moments in Earth's history. So thank you.
Thank you, Katie. That's great. And there is much applause symbolically across the across the Zoom, the planes of Zoom. So people who wish to ask questions, you can raise hands. We're starting to get some, and you can also ask in the chat. We have one question from Thomas, but I just have to make sure that everyone is able to unmute themselves, and then go ahead, Thomas.
Thanks, Louis. Hi, Katie. Katie, thank you for the talk. I'm just wondering about your what you said about how cratonic thickness is determining their longevity and their stability. What would you say to someone who would argue the opposite? Who would say that Cratons are actually thick because they are stable and long-lived?
Right, and I think it goes back to what I was pointing out before when I said the stability is likely linked to having this thickness with there. And so, I mean, when you then look at what are the surface observations saying, what are the below saying, and it really does seem to be that when you look at it from below coming up, that there's commonalities coming from the thickness itself. But I mean, you could also say it does take time to move a thermal boundary layer, have cooling going through that thick, chemically depleted root. So there's some timing that takes place there. But again, looking at the age range of the keels that we do have, it does seem to be happening within the Proterozoic and Archean. So they became thick and then they stayed that way, rather than they became thick because they were around a long time. That's my thought.
Anybody else would like to ask a question? Go ahead and raise your hand, unless it's one of the hosts. When you can't, you just have to butt in. Okay, so I have a question, which is just related to the specific geometry that you brought up in the second half of this work, which has the sort of subduction zones rolling past the sides of the craton, I guess. And do you think, or is that specifically, do you think, more likely to be the interaction that occurs between subduction zones and the cratonic lithosphere? And do your conclusions sort of carry over if it was more of a sort of frontal assault?
Right. I think that that is a great question. The reason why we picked this one, because we thought it would be a cool idea, since we already know that there is seemingly flow that's being channelized along there. So it's kind of idea is like if you hit it with the hardest and most extreme case, what would happen? But typically what we do think of Cratons is from the more direct, that you're subducting something underneath it or by it, nearby it. And so what I like about testing in this case is that you aren't necessarily asking the subducting slab to do something else like rehydrate the root or metasomatize it, or doing these interesting things that then would change the rheology with it too, which then you would have another factor to play in. But that is kind of the next step, is then put these into fully dynamic settings where you could have subducting slabs then coming from the side rather than going at a strange 3D kind of approach with it too. So we'll find out.
Thank you. Are there more questions?
I have one. When we're moving these lithospheric plates around, we're often melting and eroding. And I'm wondering how you think you might incorporate those aspects into these models.
Into the ones based on shape, or just in general?
In general.
In general. So that's what I like about using the stability regimes, because then you can start thinking of like, well, what would be the consequences if you then had refertilization happening through melting or something like that? That could then change the overall buoyancy of the material too. And so then you could say, well, if I expect to see a change that would be associated with this much change in buoyancy, would I expect it to move into a different stability regime and then predict deformation? And that's what I think is kind of the power of thinking about and using stability regimes rather than just solely relying on simulations only. So you can explore those fun ideas.
I guess the follow-on question then is, do you expect to see a lot of change once you do start including melting and erosion?
Depending on whether or not you could have, this is another caveat as well, is then depending if you have a really thick root there, you're limiting your overhead for decompression. And so then you might actually be not making it very easy to melt depending on where you're. If you're near the margins, it might be easier to have melting happening, to have that interaction, and then that could feed in, and then you could then have even more potential thermal erosion.
Cool, thanks.
Yeah.
Thomas, if you have a second question, that's fine.
Thank you. So I was just more like a very simple question. I was wondering, so you mentioned those edge-driven convection cells around the Cratons, and you said that you increased the size of the glyphs 10 times. Do you have in mind the actual magnitude of the flow around there? Like, for example, I don't know, downwelling or an upwelling current, like what kind of magnitude it is?
I don't recall the magnitudes off the top of my head, but to give myself a plug, the paper's coming out in February, so feel free to read it, so that way you don't have to rely on my memory.
All right, thank you.
Or you can email me and I can send them to you, either way.
Thank you.
Okay, Patrick, you have a question. Go ahead.
Yeah, thanks. Thanks for the talk. It was great. My question is about how at a point in your talk you showed that Mackenzie picture of all the Cratons lining up together and forming one big band, and then obviously since then they've all split apart. And although that's not necessarily destruction of Cratons, it does fundamentally change their shapes each time that cycle happens. So I was wondering if you had any comments on that to do with Craton stability and their shapes.
I'm so glad you asked. So this is where I'm working with the team to kind of move forward and to ask those questions too, is saying, okay, they're coming together and coming apart. How permanent are the shapes that we're seeing today in today's configurations? Are those shapes? Are those something that you will always see, this like strong vertical thing, or is that left over from the last splitting up opponents? And yeah, I want to know. So that requires doing more work.
Yeah, thanks.
Okay, so I'd like to say thank you again, Katie, because there's an opportunity for you to sort of spend some time with the early career and students.